We'll start though with the very basics. Hey, what's up? So the very basics is how we're going to begin this. And what I would like to start with is just like chemical energy and mechanical work. So basically, what we're going to be doing with liquid biprop engines is that you have a rocket engine that takes two components. And Edmund went over a little bit about this in the GDM, if you were there. So our engine feeds an oxidizer, and it feeds a fuel into the bottom. Now, if you don't remember, I don't know if you guys remember your general chemistry from high school, but you should have gone over like the general combustion equation, where it was, hey Brian, sorry I had to erase your stuff. I took a picture of it though. But the general equation, it's CXHY, and there's some stoichiometric amount of that, plus blank O2 yields blank CO2 plus blank H2O. And so what this does is that when you break the hydrocarbon bond, so between a hydrogen and a carbon, what that does is that you unleash that chemical energy that's stored in that. That's why we use oil, coal, whatever. Hydrocarbons have a lot of energy density. For their mass, they're extremely energy dense. And so we can actually take those hydrocarbons and we can insert energy into them to break up those bonds, and we get even more energy out. But the issue is that you have a limited amount of the hydrocarbons. That's why it's not creating energy or anything like that. So it's stored inside the mass. And what you do is you put in this hydrocarbon fuel, so this is your fuel, and your oxidizer, and you put them in, and if you put them in the correct ratio, what you'll get is a specific type of combustion. And that combustion, when you put it in here and you combust those, you create basically a static pool. It's considered isobaric. You basically create a pool of hot gas. And that hot gas moves extremely slow compared to when it gets to here. Like this is like negligible compared to the velocity right here. And so the way the nozzle is designed, this is a bell-shaped nozzle. The way the nozzle is designed is that when you hit that, you hit Mach 1. And when you hit compressible flow, you go from incompressible fluid, so like hydraulic oil, imagine it's really slow moving, this gas, compared to when you get here, when it expands, it'll increase in velocity because of the way a compressible flow works. Like usually if you have a container and you increase the area, the velocity of that gas decreases because there's more room for the gas to move, it can slow down and not hit each other as much. With compressible flow, once you pass that Mach 1, everything is inversed. Whereas if you increase the area, you increase your velocity. And this all comes down to your basic physics, where K, the kinetic energy, is equal to 1/2 m times v squared. So the most efficient rocket reaction you could ever have with combustion is the lightest mass, because that'll give you the greatest velocity. Because velocity is powered by a squared term, where mass is only it's only a single term, first order. So the whole idea between solids and liquids and why liquids are more efficient comes down to this equation right here. It's because solid rocket motors create sometimes, or like most of the time, solid phase combustion products. So instead of being gases up here, where they're lighter than solids, they'll create like aluminum slag and stuff like that, and it'll spit out aluminum powder. And that aluminum powder doesn't become gas, it's a solid, so you're spitting out hot aluminum. And that hot aluminum does give you thrust, but it's not going to be nearly as efficient as liquid or gases because they have less mass and therefore they can go faster. So the most efficient rocket will be hydrogen and oxygen, where you take out this carbon here, and you become straight H, and you don't have any CO2 anymore. And it goes from straight H plus O2 becomes H2O. And so they can combust liquid hydrogen and liquid oxygen. And inside those liquid bonds, there's a lot of energy. And so you combust those two, and you create water. So what comes out of the big rocket engines that like ULA uses, and stuff like that, NASA uses, it's all steam when it comes out, so it's actually decent for the environment. But the way they obtain hydrogen is through hydrocarbons, so it's really not that great. But the hydrogen reaction plus O2, if you guys think about it, hydrogen is the lightest molecule, right? And so when you're breaking that up and you're accelerating that hydrogen out of there, it's the lightest molecule, and that's why it's the most efficient rocket propellant. And so the actual most efficient you can ever get is monoatomic hydrogen, because usually it's diatomic, where it's H2. If you are somehow able to create H, just H, and accelerate that, you would get the most efficient rocket engine that's ever been created, but you can't do that, so that's why it's always H2. So that's the basic of what our rocket engine test stand is going to start with, is that it's going to start with a fuel and an oxidizer, and we're going to take that fuel and that oxidizer, and we're going to put it to our engine in a correct ratio so that it can burn those propellants, create a pressure vessel basically, and accelerate all of that gas that you created from that combustion reaction into mechanical work and therefore thrust. So what I'm going to go into now is a lot of the PID. So I have a PID right here for you guys as well, in case you like an electronic version. But what's important is that among our team, we understand what the symbols mean. And so that's why I threw a legend on there for you guys, so you guys understand where it's going and what we're going to do. So I'm going to start with a ball valve. So a ball valve is literally, if you guys want to look here, and I'll show the camera in a second. Oh, nice. So this is a ball valve. It's currently closed. Inside this is a stem. So this stem goes through here, and it attaches to the ball. And what that stem does is you can turn this handle 90 degrees to turn the ball. And all that does is that no fluid will be let through. You turn the handle 90 degrees, and then fluid is allowed to pass. And the reason why we like to use ball valves is because they have very, very low mechanical complexity compared to other valves that we could use. But one thing that's bad about ball valves is that you can't throttle that well with them. So throttling valves are used, they're a lot more expensive hardware, so we're never probably going to even bother with this. But they're not oftentimes used for throttling. But this ball valve, so basically what it does is as a handle, you turn it 90 degrees, and it opens and closes. It's on-off position is what we use it for. And then, so on this PID, this ball valve fail closed or ball valve fail open. So ball valve fail closed means that when the system is in its normal state, that valve will always be closed. So if you guys look at the bottom left where it says PBV FU 253, so that's the main fire valve. So that's actually when we open that, propellants will be allowed to flow to the engine. So in the bottom left, that's a normally closed ball valve. So if you guys just think about it logically, it makes sense that that ball valve would be normally closed. Because if we're filling our tanks, we don't want that ball valve to be open all the time, because then we would have propellants flowing straight into our engine. So you don't want that. So what you really want is that to be closed normally. The only ball valve set that we have on this plumbing and instrumentation diagram that's open is the vent. And the reason why that's normally open is because if we're traveling and stuff like that, or you're in the middle of a fill procedure, you have a lot of dangerous vapors and gases that come off of these propellants that you're using. Like liquid oxygen will vaporize and create gaseous oxygen. And if you let that sit for a while, what's going to happen is that it's going to pressurize your tank on its own. So the reason why you leave that vent open is to let that gaseous oxygen out. And so it doesn't pressurize your tank while you're filling, because it's dangerous to be near a pressurized tank. So it's a safety concern, and it also lets us fill liquid in there, because eventually if you just fill liquid in there, the gas oxygen on top and the liquid oxygen on bottom will be at an equilibrium before you fill up your liquid oxygen all the way. And so you won't be able to fill your propellants anymore if you leave your gas just sitting in there. So that's why we vent it. So that vent is normally open. That's normally always open, especially while we're filling, because you don't want that pressure to build up. So that's the only ball valve set that's normally open on the system. To go to a check valve, what a check valve does is, you guys look at the PID, it takes flow in only one direction. So wherever that triangle point is pointing, it's only going to let flow in that direction. So if you guys look in the top left, check valve N2 270, what that does is that's going to take nitrogen gas from all the way from that K bottle up at the top in the middle, and that's going to let flow in only one direction. So that means that no nitrogen past that check valve is going to go backwards into the K bottle or backwards into our regulators. And the reason why we put a check valve there is to protect your mechanical components, because these regulators are sensitive devices and you don't want backflow going through them. And also with your valves, you don't want pressure to go backwards on your valve. It's just not necessary, and so don't risk it. And so that's the reason why we have check valves. So check valve lets flow only go in one direction. And you can have check valves that are made differently. Sometimes they're made for only gases, sometimes they're made for liquids, sometimes they're made for cryogenic liquids, which means extremely low temperatures. Then we have a pressure relief valve. So you got to calculate these things, and basically what a pressure relief valve has to do is that if your pressure vessel, which is that kerosene 750 psi tank, or that liquid oxygen on the right-hand side, 650 psi tank, if those pressure vessels get over-pressurized, they could burst. And so that pressure relief valve is a functioning safety mechanism. So what happens is we calibrate that PRV, and we say, okay, we know our tank's going to explode at 2,000 psi because we did previous testing or something like that. So we know that we don't ever want to go past 2,000 psi, and actually we don't even want to get close to there. So let's say at 1,500 psi, we're going to calibrate this pressure relief valve to open at 1,500. So if there's ever an overpressurization event where the tank pressures gets way higher than we designed for, that pressure relief valve will kick open and it'll expel all those gases to avoid the tank getting overpressurized. And a lot of the safety concerns that NASA had with our current system is that our pressure relief valve needs to be cryo-rated and liquid oxygen rated. Because what happens is that when you vent, it vents whatever gases are inside of that tank. And like I said before, you're going to have gaseous oxygen in that tank. And gaseous oxygen is ready to combust. It's a heavy oxidizer, and it can ignite very easily. So pressure relief valves, when they bang open, they literally bang and pop, like you can hear it. And that banging motion, it'll close, and then it might bang open again. And that repetitive open and closing, you could be clapping that oxygen, and it'll blow up. And you'll create a blowtorch, basically, when you're not intending to. So that's a very critical part about pressure relief valve purchasing and getting the right part. The next thing is...
How do you pick one that doesn't have the risk of...
They have certain seals in them that won't do that banging action, that won't ignite when it's in contact with that oxygen.
Gotcha.
Yeah.
Do you only use PRVs for tanks?
Yes, you only use pressure relief valves for tanks. One of the questions that the CubeSat had, this is where this is coming from, is that could you use a pressure relief valve for a tube? You absolutely could if you wanted to release pressure from that tube. But the thing is that our tubes are filled with liquid usually. And so if you were to kick open a pressure relief valve and it was liquid, you would have liquid spewing out of your system. And that's usually a combustible fluid. And so if that's happening, you're spraying a combustible mixture into the air. That's really dangerous. What they're worried about is that hydrogen peroxide, it vaporizes, and it can create a pressurization just like liquid oxygen to gaseous oxygen. And they don't want the tubes to burst. But I don't think that's a design constraint that they're going to have or need to worry about. That's for like bigger systems that they need to worry about that. The next on the list is the Cavitating Venturi. So this is basically the choke of our system. This Cavitating Venturi, we are going to size it perfectly. So basically it has a small hole through it, and we make it so that it has a bunch of fluid on one side of it, towards closest to the tank, that's upstream. And downstream of it, we let it trickle out. And that trickling out, I mean, I say trickle, but it's really flowing really fast. So that trickling out, we're going to be able to tell exactly what goes into that Venturi and what comes out of that Venturi. And the way you design these is if you have a 15% pressure drop across it, so if you have 100 psi and you drop down to 85 psi, then you can use a certain set of equations called the cavitating flow equations to know exactly what your flow rates are. And knowing these flow rates is very critical for when you're testing your engines, because you need to know your exact inlet mass flow rates, and you need to know exactly what's going into your system and how fast it's going. And the reason why you need to know these values, it gives you your engine efficiency, it gives you your engine combustion pressure, it gives you engine chamber, that's the engine chamber pressure. But basically that's what why you need the cavitating Venturi. So the way we're designing the system is that we have this Venturi basically take up a bunch of flow, and then we're on purposely choking it through that Venturi, and then when it comes out through the outlet, we know exactly what's coming out, so we can control the flow that way. Next on the list is a solenoid actuator. So a solenoid actuator is
basically we use ball valves that a solenoid is you induce an electric current through it, and it creates a magnetic field, and that magnetic field will actually pull up a pin, and that pin will lift up and it'll let fluid flow underneath that pin. Usually that pin's blocking the way. But what's going to happen is that when you send an electric signal to that solenoid, it's going to open up and it's going to let flow through the bottom. And so actually I have a video on the computer that I can show you guys. Let me see this real quick. And so we can actually link these when we publish this video to the rest of the team. So this is a direct acting solenoid valve. So the switch closes, lets current go into the solenoid pulls up that pin, and then lets out the flow through. So originally, there's flow through this bottom part, and this pin is blocking everything. When you close the switch and electricity is allowed to flow into this solenoid coil, it'll lift up that pin due to the magnetic field, and this pin will open and go upwards. When that pin goes up, fluid can flow through the solenoid ball valve. But it's not really a ball valve, but we use a blown valve. And so now pressure can flow through, and you can have your fluids flow. Fluids, excuse me. That's a solenoid actuator. The spring return pneumatic actuator is what we are going to be using for the fire valve, the main fire valves 253 and 353. And we'll be also using spring returns for valves 251 and 351, as well as 151 and 150. So all these valves are spring returned pneumatic actuators. So what this means is, I actually have a demonstration of this as well. This device here is a pneumatic actuator. This one in particular is double acting instead of spring return. So what happens is you put pressure into one port, and it'll let this bladder expand basically, and it'll turn this piece 90 degrees, which turns a stem, and that stem will turn your ball. So you put pressure into one port, it'll turn your ball one way. You put pressure into the other port, it'll close this, it'll turn the stem the other way 90 degrees, and it'll close your ball. This is a double acting pneumatic actuator. So you put pressure into two ports. The difference between double acting and spring return is that spring returns only have one port. You put air into the middle, it'll open that, and then when you take air out, the spring will close it for you. It's more secure that way. Instead of depending on air pressure to close it, you're depending on a mechanical force to close that thing, and so you're sure that it turned 90 degrees. And the reason why we'll be using spring returns instead of double acting on the new system is because we're more confident that they're closed, and also timing them is easier. They'll have a more consistent timing. And I have an animation for you guys as well for spring return. This is a spring return pneumatic spring actuator. And so you guys can see this is the first port down here. And the second, this is only one port because it only lets fluid in one way. So when you let fluid in, it goes into the middle and it pushes this bladder open. And so it'll turn those cogs and those gears, and it'll turn that ball 90 degrees for you. When you take air out of that and you suck it out, the springs want to force that thing closed, and so it'll close automatically. So it gets the on command, air will flow into the middle, and it'll push those springs out to the sides, and it'll turn that cog 90 degrees for you. And then you give it the off command, and it'll take air out, and that pressure differential will let you close this. This is a little bit different because it lets air in both ways, but this is just a special one, so don't worry about that. That's not how ours works. And then if you guys wanted an animation about how a ball valve works, how it looks like with actual fluid flow, this is what our propellants will be. This is how it's acting. So all the propellants will be sitting up against the ball like this. So the ball has to handle a really high amount of pressure. We're talking 750 psi, 650 psi. So that ball has to hold back all that really high pressure fluid. And when you turn that ball 90 degrees, it'll let the fluids flow through it. So it's just as simple as that. It's on-off sequence. That's all it is. And there's a bunch of technical stuff that goes into these valves. There's like seats and seals. So basically, you never have to worry about your ball leaking. Because if this leaks, you'll be sending propellants to your engine when you don't intend to. And you might cause a rapid disassembly of your engine, as the NASA guys would say it. So next on the list is a manual actuator. So that's literally like this hand valve right here. This is manual. You literally turn it by your hand. This is be our fill procedure, so we're going to have manual actuators. You'll see on the bottom left and bottom right, fill fuel and fill aux. And so those are hand ball valves. That's what HBV stands for. So 252 and 352. Those will be by hand. And so somebody is going to have to go up to the system when they're filling the system, turn the valve by hand, and then they're going to let fluids flow through that ball. And the reason why we do it by hand is because it's not really a safety risk and it's a lot cheaper. So it's just better to do it that way. Then next on the system, we have a pressure regulator that's hand loaded. And so hand loaded regulators, I don't know where, okay, they're over here. Can I lift up? No, I'm not going to bother lifting that up. So basically regulators, what they take is they take high pressure, high velocity fluid, so such as nitrogen gas. And so this nitrogen gas at 2,800 psi, if you guys look at hand-loaded regulator N2100 at the top in the middle, so HLR N2100, this hand-loaded regulator, we're going to turn a dial, and we're going to set that dial to a specific turn. And what that does is it opens and closes a spring inside there, which allows a certain amount of fluid through, or chokes that fluid. And so what we're going to be doing is we're going to put nitrogen gas at 2,800 psi, and out of that regulator, it's going to become like around 150 psi. So it's going to take 2,800 psi and regulate it or control it down to 150 psi. And so that's what regulators do. You guys are probably already familiar with them already. They have a lot of mechanical complexity with them. They're very expensive. And so the way they're made is that you have a 1/4-inch MPT in, which is just a national pipe thread, and then our dome regulators have 1/2-inch out. So it takes a small input and makes it a big output. So you get higher velocity gas at a lower pressure. That's how we reduce all the pressures in the system. And the reason why we need to regulate flow is because a lot of these devices, these ball valves, these tubings, these tanks, can't handle 2,800 psi. That's a lot of pressure and a lot of force. And so we regulate it down so you guys don't have to, so the parts don't break basically or don't burst. So that's why we regulate it down. And also in the end, when you're sending propellants to your engine, you don't want to send 2,800 psi worth of propellants to your engine. You want to send a very controlled pressure, and that depends on your injector design. And so you want to send a very controlled pressure, and that's why we regulate it down. The pressure regulator dome loaded. So dome loaded regulators, if you guys look at the SFS up at the very top there, that big, this component right here is a dome loaded regulator, and then this one's an inline regulator. What happens is you put a memory into the top of that dome. So if you guys look at the diagram, DLR N2200, it's in the middle. So that dome loaded regulator takes nitrogen gas, and what you're going to do is that you're going to put a memory into the top of it, and that's going to be a hand-loaded memory. So someone's going to be literally sitting on the system, and they're going to start at 5 psi, they're going to turn it once, go to 10 psi, and they're going to go all the way up until they hit 750. Once they hit 750, that regulator, that dome, is going to know that when I get flow, and when I get pressure, no matter what pressure it is, because you put 750 into the top of my head, I know that whatever comes through my bottom has to be 750. So what's happening is that this nitrogen bottle at 2,800 psi is going to let nitrogen through that dome load at 2,800 psi. And that's a lot of pressure. But these dome loads can handle about 5,600. So what's going to happen is it's going to take 2,800. It has a memory for 750. So out of the side of the regulator, it's going to let 750 out. So we're going to regulate it down from 2,800 to 750. That's what that regulator does. Any questions on dome load versus hand loads?
Yeah. So why are you using both and not just like a hand load?
So we could use a more expensive hand load just individually. These dome loads were donated to us. They're about $590 a pop. And so that's why we don't want to buy new ones. The flow coefficient, so how much fluid flow rate these dome loads has, is significantly higher than the hand loads. Just the way they're mechanically designed. What happens is that this regulator, the hand loads, lets about 8% of your flow through, whereas the dome loads let about 96%. So it's a difference of cost and it's a difference of mechanical complexity. So that's why we have the hand loads be the memory. And we have the dome loads actually flow our fluids that we care about because we don't want to choke it too much before it gets to the Venturi. Because if you guys flow fluids too slow, then you're not going to have enough pressure in your tank to maintain that constant pressure feed. Then we have a 3-way solenoid valve. Okay, so I actually don't have a diagram for this or one out here. We have a bunch of 4-way solenoids, but basically what happens is if you guys look at solenoid valve CG451 in the left, next to the fuel vent, that has one port in and one port out. That one port in comes from a compressed gas at 150 psi, and its one port out will be 150 psi as well. And that will go into the pneumatic actuator that is the pneumatic ball valve. A 3-way solenoid has 3 ports, one in, one out, but one vent. So that vent, basically when you turn off the solenoid, instead of sending that gas and like letting it sit inside that line pressurized, it'll vent that line for you. So it basically prevents any residual pressure inside that line. It basically allows us to turn off the pneumatic ball valve. That's why you need a 3-way. If you had only a 2-way, the issue with only having a 2-way is that it... Damn, Brian. Damn, he's angry. Yeah, you can close it. Just crack it. Yeah, thank you. So that the reason why you can't use a 2-way solenoid is because it has no vent, and it would allow pressure to be locked in there. You need to crack it so you can come back in. Yeah. So that pneumatic ball valve, so that solenoid, that's what that does. That's a 3-way. There's also 4-ways where you can have one in that's in all the time, and then there's 2 outlets. And when you actuate the solenoid, it'll open the second. So that's how these double acting ones work. So what basically happens is that you have a 4-way solenoid, and it has 2 outlets. One outlet goes into the in of the pneumatic actuator, one outlet goes into the out of the pneumatic actuator. And so what happens is that when you power that solenoid, it has an always on state. So it'll always be like permanently closed for this. And then when you actuate that solenoid, when you turn it on with electricity, it'll let fluid flow through the other side and it'll close it instead. So that's the difference between 4-way and 3-way. The choking orifice, this literally is just going to be a piece of metal with a hole drilled through it. And the reason why we use choking orifices is to control the flow rate that we have. On the purge sides, this is mainly why we use a choking orifice, is because when you purge your engine, and by purging, what happens is at the end of your test, you need to make sure that you push all the propellants out. And if you have a bunch of high pressure fluid in here and it escapes, you run the risk of, when it leaves, of running a vacuum inside your engine, of being lower pressure than the atmosphere. So atmospheric pressure is 14.7 psi. So if you ever get below that, what happens is that all the pressure of the atmosphere wants to come back in. And that's going to cause a lot of stress on your engine. And to avoid that stress and possibly destroying your engine, we purge it. And so we purge it at like 150 psi or whatever it's going to end up being calculated to be. And so these orifices allow us to push the exact amount of fluid that we want to push out in order to get those last amount of propellants through. PG in a circle, it stands for a pressure gauge.
Yeah. Are the choking orifices kind of like low-tech versions of the cavitating Venturi?
Yes.
It just like regulates the flow by choking it?
Yeah, we're just going to choke the flow on purpose, and we're going to drill that orifice to be the exact dimension that we want it to be. The difference between a cavitating Venturi and that orifice is that the cavitating Venturi is shaped in a very special way. It's basically, it looks like a tunnel. And inside that tunnel, there's like a little choke like this, just like this tube is shaped on here. Whereas the orifice is literally going to be a piece of brass with a hole drilled through it. So it's a lot different in that regard. And the Venturis will let us get flow rates where choking orifices, we're going to have to dimension them properly so that we know what we're getting, but we're never going to be able to measure from it. Pressure gauges, you guys have seen them everywhere in your life. Basically, it's just a mechanical dial, and that will move based on what the pressure is reading. And I'll talk more about the positioning of our gauges. A pressure transducer takes that pressure that you put up against that transducer, turns it into a Hertz signal, and then we can read that Hertz signal and transform that Hertz signal into a flow rate or a pressure. So that pressure that we're going to be reading is going to be a static pressure. So if you guys have taken fluids, you'll know the difference between dynamic and static pressure. And that static pressure that it reads, it'll give a bunch of frequency basically, and we read that frequency, filter that noise, and then we can know exactly what our pressures are. It'll be identical to the pressure gauge, except it's an electronic sensor as opposed to a mechanical sensor. A thermocouple, what a thermocouple does is that it reads temperature basically. And so it'll send that temperature data. I'm not sure if it's in a Hertz signal or not. Dennis will have more info about that. But a thermocouple basically just reads temperature electronically, and so we can read it on a computer.
I think it's just a voltage difference.
Oh, a voltage
by
difference?
The Seebeck effect, yeah.
Okay, cool. Thank you. So it's a voltage difference based on the expansion, right, of the thermocouple or something like that? Because it's made out of copper usually?
Yeah, usually there's like two separate metals in there.
Yeah. Oh, the voltage is between them, right? Like as they get farther
Yeah,
apart?
because you have two different metals, and so then you're going to have some potential between them based on the temperature.
Cool. All right. So that's how thermocouples work. And then the F, the big F with the rectangle, is just a filter. So that filter basically takes a bunch of debris and it traps it inside of it, and so that debris doesn't travel through your system. It's very important to keep debris out of your system. So once we get this system cleaned, the entire oxidizer side has to be cleaned off, because oxidizers will make fuel out of anything. I mean, NASA showed us a bunch of videos basically where the valve they had, it was holding like 75,000 psi. It was absolutely massive. And when it opened up, it was vibrating just a little bit. And that oxygen, when it comes crashing in through that valve, that vibration caused enough friction to ignite that liquid oxygen. And so it made the metal of the valve a fuel itself, and the valve just blew up. And it started melting, and then the engine blew up, and it was like total catastrophic. And so that's why you need to keep debris out of your system, because that debris, if it's traveling through your system and hitting elbows as you're traveling at 20 feet per second, 16 feet per second, if you're crashing with that debris, it could cause friction or ignite that liquid oxygen that is traveling alongside. And so you want to avoid that situation from happening. So that's all the components of the plumbing system. So I'm going to go through and like systematically talk about, yeah, you have a question?
Yeah, does the filter factor into the thing you said about not running your liquid oxygen at more than 25 feet per second?
Does it filter, what do you mean, does it factor in? Does it slow down our flow?
Is that part of the reason why
You
don't
keep it.
run?
Yeah, the reason why you don't run liquid oxygen past, well, you're never supposed to run it past 60 feet per second. And the reason why we're going to keep it below 25 is because liquid oxygen, when it like crashes into tubes and it's making a bunch of bends and turns, you have a lot of head loss that way. And so you want to go kind of as slow as you can, but keeping that pressure. And so you want to avoid head losses by going too fast, and the debris won't ignite if there is debris in there. So that's why you keep it nice and slow, comparatively. Does that answer your question?
Yeah.
Cool. All right. So I'm going to walk through this system. I'm going to color it on my computer, and I'll color it on this too. And so what's going to happen is, the procedure for this is that we're going to have a bunch of propellants filled up. So propellants are going to be stored inside this engine, and you're going to fill from the fill aux. So we're going to fill up our oxidizer first. So when you fill your oxidizer, what's going to happen is that you're going to go through this tube right here from outside the system. So we're going to go ahead and color that. Oxidizers are usually green. We'll color it green. Oh god, you can barely see that. Okay, I'm not going to color it on that. I'm going to color it on this diagram. Okay, so when you fill oxidizers, all that green section, when we fill this system, okay, so this green section right here, all the way from the pneumatic ball valve, that's our fire valve, all the way up into the bottom of your tank is going to start filling with liquid oxygen. Because there is nothing stopping it from flowing that way. There's no valves or anything besides this valve, and it's slowly filling up this tank. And we're going to know to stop filling this tank based on our vent temperature, and we're also going to be able to tell it through the pressure gauges. So that's how we're going to know to stop filling. So that's that's going to be filled when we start filling that oxygen, that liquid oxygen. And then
where's the liquid oxygen coming from?
The liquid oxygen comes from a dewar, and we buy that dewar, and a dewar is basically a big, huge-ass tank and it's held at 22 psi. We just turn a dial and liquid flows out. And so it's pretty simple to use. Liquid oxygen can get pretty expensive.
How is that represented here?
How do I represent that liquid oxygen's there?
No, the way it is coming from. Like, is there which valve?
So
Do it.
to represent that something's coming outside the system, it's a straight line with a vertical bar. So if you look at fill ox, you'll see that straight line with that vertical bar to indicate that it's coming from outside the system. And if you look at your vents, it has the same exact symbol, meaning it's leaving the system. So it's just outside of the system, so you don't have to worry about it anymore. Now, your fuel, if you look at your fuel side, and you look at your fuel fill, it's exactly symmetric to your liquid oxygen side. So you're going to be filling up that whole side all the way down to that fire valve through the Venturi, and you're going to be filling up some proportion of your tank. We like to pre-measure our kerosene amount so we know exactly what our burn times are. And so, do you guys want me to show you where this is filled? This is just as symmetric of the oxidizer side. So that fuel is filled up all the way up in there. And so what happens is that because liquid oxygen is cryogenic, which means that it has a boiling point of like negative 300 degrees Fahrenheit, it takes a while to fill liquid oxygen because you have to chill down your whole system basically. Because our system will be running at desert temperatures, I'm not going to call it room temperature because it's definitely not 70 degrees out there. So our pipes are running about 80 degrees Fahrenheit. And so what happens is that that's a 400 degree difference almost between the liquid oxygen dewar and your pipes and your tanks. So we had to put liquid oxygen through the system, and as soon as it hits those tubes and pipes and tanks, it vaporizes because it boils off. But that action, eventually, after a long, long time, after an hour and a half, our system is going to get cool enough, our tanks are going to be insulated, and so they're going to be at that like negative 275 degrees Fahrenheit range eventually. So it could take 45 minutes, an hour to fill this. Vulcan, we're going to have probably almost 2 hours to fill those tanks.
Is that what cold flow is?
Yes, that's exactly. We fill it with a cryogenic liquid nitrogen. And so liquid nitrogen has a lower boiling point than liquid oxygen. Liquid nitrogen is like negative 330 or something like that. So it's a good indicator of how liquid oxygen is going to fill. So that's why we test with liquid nitrogen. There's no need to test with liquid oxygen. It's more expensive, and also it's dangerous. Nitrogen's inert, so you don't have to worry about it blowing anything up. And so what happens during the fill procedure, our whole system's hooked up, for example, it's on the I-beam, and if you don't know what an I-beam, don't worry about it right now. And we'll fill the kerosene side. And so we literally have a kerosene fuel tank. We fill it with kerosene. We close it up. We pressurize it to 30 psi. We open a manual ball valve on that. Fluids flow from our little manual tank into our system. And we know that based on a pre-measured amount, that's how much kerosene we have inside the system. Kerosene doesn't vaporize. We don't have to worry about it boiling off or anything like that. And then after...
Does that mean that you're going to start the liquid oxygen first?
No, you can fill them at the same time, really. It doesn't matter. But usually we only like to have 2 people on the system filling liquid oxygen, just because the fewer people you have around it, the less dangerous it is. And so we usually fill kerosene while the engine's being mounted. And so it's like 3.5 hours before we even fire, really. So the kerosene sits there for a nice and long time. A lot of stuff that other companies do is that they let the kerosene sit for like an hour and a half. Because a lot of that bubbling in and everything like that, and there's little gases inside the kerosene, like little air bubbles and stuff from you pressurizing it to the 30 psi. They'll let it sit down and relax for like an hour and a half, and they'll keep the vent open, so you don't have to worry about any like weird like burps going through your test or anything like that. So you'll fill kerosene, then you'll fill liquid oxygen for like an hour, and after your liquid oxygen's full all the way, what happens is that you have a system now that is filled with propellants, but it has nothing to send those propellants, nothing to motivate them to go to the engine. Everything for terms of pressure flows from high to low, right? So if you have a high pressure K bottle, which a K bottle is just the size of it, so this nitrogen 2800 psi bottle is filled with nitrogen gas.
Is there a reason you pick nitrogen over like helium?
So yes, helium's way more expensive. It's about $960 per bottle. Nitrogen's like 80. And nitrogen is an inert gas just like it, and it's a little bit heavier than helium. Helium flows a lot faster. And helium creates a lot of dangerous situations, especially with pressure relief valves. So if you were to open a pressure relief valve with helium versus gaseous nitrogen, when it breaks open, it could cause a lot of damage because it wants to flow out so fast. And so nitrogen is a little bit more safer because it flows a lot slower. And we don't have to worry about solubility issues with N2 and O2, because I mean, N2O is an actual molecule of nitrous oxide. It's laughing gas, but that reaction won't occur inside of our system for a while, so we don't have to worry about it. Just don't let nitrogen sit on top of your oxygen for 4 hours, and you're fine. If it what happens is we pressurize our tanks and we fire within a minute. So now I'm going to explain the pressurization system. So the pressurization system looks awfully complicated. So this is the most expensive portion of our static fire system. Because I mean, if you look below the tanks, it's literally one valve and a Venturi. That's not nearly as expensive as regulators, vent valves, another pneumatic ball valve, check valves, pressure reliefs, pressure gauges, and all a bunch of crazy stuff like that. So I'm going to start with the way this works, is that we have our nitrogen K bottle. It has a hand valve up top. So when the person's ready to start regging up the pressure system, what they're going to do is that they're going to open the K bottle. It's going to let 2,800 psi flow through. So I'm going to go ahead and color exactly everything that gets pressurized as soon as you open this. So it's a pretty big volume. So everything in purple up there. When I open that K bottle, the only thing that's going to stop fluids from flowing are ball valves. So you're going to stop at your first ball valve, and you're going to stop at your second ball valve, and then you have two purge ball valves over here. So you're going to have one ball here, one ball here. So that's where your purge gases are going to stop. I mean your nitrogen gas. That's where it's going to stop first. Okay? So that's where it's sitting up against. It's sitting up against all those ball valves. And so that gaseous nitrogen is going to be pretty decently high pressured when it comes out of that bottle. So the first thing we do is when it comes out of that bottle is that we have a stainless steel tube, because stainless steel can handle higher pressures than copper or aluminum. And so we're going to have a stainless steel tube coming out of this nitrogen bottle. And the way the fluids are going to flow is that the gas is going to go into a cross. One direction of that cross is going to go to the purge system. So that's the system numbered 100s. That's your purge system. So that's basically like a bypass. It's going to bypass all the other mechanical complexities. It literally goes to one ball valve, through one orifice, and then into your engine. That's what the purge does. It bypasses everything, and it's a shortcut. And the reason why you do that is, once again, to avoid pulling a vacuum at the end of your hot fire.
Sorry, where is this purge?
Why is it purged?
Where?
The 100 series, so anything numbered would be hundreds. So you have a purge on your kerosene side, and you have a purge on your liquid oxygen side. And the reason why we have to separate those systems is because into our injector, there's different mass flow rates. So you need to control the purge sides differently. Any questions about the purge? Okay, going along the purge, you'll see pressure transducer N2 120 and pressure gauge N2 130. So these pressure transducer and pressure gauge will let the person who's operating the system know exactly what our purge pressures are. And that's important because if you overpressurize your purge, then you could all of a sudden send liquid oxygen at a way higher flow rate than it should have been. Or if you underpressurize it, you run the risk of coughing your engine up. And so you might have combustion instability, stuff like that. So you want to avoid that. So it needs to be the perfect mass flow rate. And so those pressure gauge and pressure transducer will let us know the perfect mass flow rate. Now, in the other side of that cross, you go further down and you have the 200 system, which is your fuel side, and your 300 system, which is your liquid oxygen side. These are almost identical systems, so I'm going to go through the fuel side first. So what's going to happen is that that nitrogen gas is going to flow through the bottom of a dome-loaded regulator. That's regulator 200. So it's going to flow through the bottom of regulator 200, and you do a little bypass, basically, a little tee-off to go to the hand-load regulator. So that's literally going to be, someone's going to be on top of that system, turning that regulator to change what the dome is outletting at. So you don't want to start your dome, and we could pre-calibrate it to is what we do now, is that those inlines, we can't change those while we're on the system. Those are wrench tightened. This is going to be hand dialed. So when we open our old system, what happens is that we have that 750 PSI coming out of our dome, like kick straight into the top of our propellants. And that actually is really dangerous because it can cause it to geyser. Because I mean, you have a 750 PSI brick of fluid just coming down and hammering on top of that liquid. And so it's just dangerous. We don't want to deal with it. It can cause a lot of different issues. You wet the sides of your tanks, a whole bunch of stuff that we don't want to worry about. And so what we're going to do is we're going to slowly reg that up. And so what's going to happen is that when that person is ready to reg up, which by reg up means turn the dials of that hand load, pneumatic ball valve N2 250, that is going to be open. Okay? So that's going to let nitrogen flow into the top of that tank. So that's going to be open, and you're slowly going to start like 5 psi. 5 psi will be sitting on top of my kerosene now, and then 10 psi, all the way up, slowly and slowly, all the way to 750 psi, which means that you're going to have someone with their face and their body right next to a 750 pressurized system. That's a safety risk we're going to have to take, but that's just the reality of it. There's more like $3,500 computer-loaded regulators that you can do from afar. You can like tap a button, and it'll go up 5 psi. Tap another, and it'll go up another 5. But we can't afford that.
Could you explain the whole thing again? So you're saying that this valve here gets open?
Yeah. So, say for example, all our propellants are filled, and I opened my nitrogen bottle. Right now, my regulators are regulating at the lowest they can possibly go, probably 5 psi. And now I'm going to open my pneumatic ball valve N2 250 from the bunker.
So it's going to be receiving a really low pressure,
Yep.
and it's just going to be open while you're changing the regulator higher and higher and higher pressure.
Correct.
Okay.
So you're slowly going to press that kerosene. So it's going to be called a slow press. So that pneumatic ball valve is going to be open. You're going to slow press that kerosene. And then after your regulator, you need to know exactly what your flow rates are out of your regulator, because you don't want to be pressurizing something that you're not familiar with. So that's why you have that pressure gauge 230 there and pressure transducer 220. That'll tell us exactly what our regulator output is, and that's very important to know so you don't overpressurize your tanks and blow up your tanks.
Wait,
yes.
Quick question. Why do we have both the hand valve and the
dome load, right? So dome loads, you need to put, so say for example, this is my dome loaded regulator, okay? I have, coming from my 2800 PSI K bottle, I have 2800, 2800, 2800, and it hits the inlet, okay? Whatever pressure I put into the top of my dome, so think of a dome, like it's up above, whatever pressure I put into that memory is what it's going to let out through the outlet. That's how these things work. So you need to have a pressure into the top of the outlet. So if I start at 5 psi, it's going to let 5 psi through. If I turn my hand load up here to 10, it's going to have 10 inside this memory, and it's going to let 10 out.
Also, the hand one is the set, the dome.
Yes, the hand load calibrates my dome, basically. Yeah.
I forgot to take my medicine this morning. So
Okay,
I'll be back.
you're good. All right. So that'll be slowly open, slow press. Also, one thing about this is that look at your pneumatic ball valve N2 251. That's your vent. If I were trying to pressurize my system and I had my vent open, I would literally be wasting all that nitrogen gas because it would go straight into the atmosphere. So I need to close that ball valve. So this is a closed system now. Now, going along the line, check N2 270. I already explained how check gauges work. So that's going to be, it's going to let nitrogen gas flow in only one direction. Now above my tank, if you guys look at pressure gauge 231, pressure transducer 221, and pressure relief 280, I already explained those. But basically those are going to hold static pressure. That's going to give us our tank pressures right there. That's how we know exactly what's inside our tank. That'll be important to know our mass flow rates to our engine eventually.
John, so
Yeah.
you have a pressure transducer right after the regulator and then just above the tank.
Yes.
That's just to account for the pressure loss in that pipe?
Yes, it's pretty redundant.
Okay.
Yeah, but mechanical redundancy is better than playing games and risks. And so what happens is that you basically create a pressure boot on top of your kerosene tank. So all that purple that you see on top of my kerosene tank, that's what happens over time, is that eventually that goes from 5 psi all the way up until that 750. And so I keep regging that up, and I get to 750 eventually.
John,
Yes.
real quick for the pressure regulation there, is that by our, that's not by the ball valve, right? That's by the regulators. We do it 5 psi at a time.
Yes, you're gonna turn your hand load knob, just little turns at a time, to slowly pressurize your system. The ball valve just lets fluid flow through or not. That's an off-on system. That doesn't regulate anything. Cool?
Yeah.
So, yeah.
Also, when we're filling the pressurized nitrogen,
Yes.
do we close off the other valves that we let in for the compressed gas?
Do we close the other valves, such as...
Like the PBV into 251?
So, when we start rigging up, do we keep
Yeah.
250 closed?
Or 251?
251.
Yeah, because isn't that what comes from the
Yes, you are going to close 251.
when you switch off to pressurized?
When you start pressurizing your system, you need it to be a closed system. Otherwise, you're going to evacuate all your gases and waste pressurizing gas. Good question. Okay, so now we created basically, if we'll just take kerosene by itself, okay, we created a propellant system that's sitting up against the valve with the 750 psi fluid above it. And so everything wants to flow from high to low. And so because the pressure above that 750 is eventually 2800, when we open valve 253 in the fuel side, when we open that, it needs to flow towards the engine. It has no choice. It can't flow backwards. That's the way it's designed, is that everything flows from high to low. And so
you have that check valve as well.
yes, and we have a check valve to prevent any backflow. Correct. So that check valve is just there in place to protect us. So when we say fire, valve number 253 is going to open, and that propellant is going to flow, and I'm going to draw this in black so it's a little bit different than the fill procedure. That propellant is going to flow all the way to the base of our engine. So everything I just scribbled out in black over here. So when I open pneumatic ball valve 253, this is where it's going to head out to. It's going to head out straight to the engine, just right there. And just so you guys know, the fire procedure will be all automated, so we don't have any human error in opening and closing valves and timings and stuff like that. So that's what's going to be fired. That's how the firing mechanism is going to work. Now, if we look at our liquid oxygen side, it's the exact same thing. You are going to have nitrogen gas flowing through, and you're just going to slowly reg it up all the way until that 650 mark. And you're going to keep your vent valve closed. And basically, it's the same exact thing. It's symmetric to the other side. One thing you'll notice about the side of the liquid oxygen is that there's a thermocouple right before the vent. And so the reason why we're putting a thermocouple on the vent of the liquid oxygen side and not on the fuel side is so we know exactly what our venting temperatures are. Because once we get closer and closer to like negative 275, negative 290, we'll have a better idea of how cold our system is. And so we'll be able to exactly know how much liquid we're going to be filling at that time. The reason why we don't need that on the kerosene side is because we pre-measured the amount. And we don't need to worry about that. So now you slowly reg up your liquid oxygen to 650. And so this pressure-fed system is designed in such a way that you will have a constant 750 or 650 psi boot pushing down on top of your propellants. On our old system, what we're having an issue with is that we're not filling up that gap of the propellants leaving with that pressurizing gas fast enough. So instead of staying at that constant 750 or constant 650, we're just going from like 750 and draining slowly to like 450, 250 until we run out of helium. And so you don't want that. That's transient, that's unsteady state, and that's different mass flow rates to your engine, and that affects your efficiency of your engine and also can cause combustion instabilities. And so it's dangerous. So what we don't want to worry about is having bad data. So we're going to get good data if we have steady state functioning. So that whole pressure-fed system is going to be our steady state. Is there any questions about the purge, the fuel, or the oxidizer, pressurization, or propellant system?
The solenoid valves.
Yeah, I'm going to explain the solenoids in a second.
Okay.
I have some questions about, like, just a question about the data capturing stuff.
Yeah, so the DAC, yeah.
Yeah, so like you're getting temperature data and pressure data. Is there a reason why you don't want to have like flow rate data as well?
So from pressure and temperature, like if you look at your Venturi tubes, if you look at TOX 390, 391, pressure transducer 322 and 353, is that, did I number that? No, I numbered that right, 322 and 323. From your cavitating flow equations, you don't need a flow meter. Venturi itself, a cavitating Venturi acts as a flow meter. If I have pressure and temperature of my fluid before and after, I can get flow rate. So it comes from the equations. You don't need P, V, and T. You only need like P and T, basically. That's what it comes down to. Any other questions about the propellant system or pressurizing system? Yes.
So how does a cold flow test, like what does that serve?
Yeah, so
Like, everyone made such a big deal about it. I felt bad, but like, we didn't really even know what it was.
yeah, so a cold flow test is different than a hot fire, and that you are sending inert liquids to your engine. They're not going to combust. All you're trying to get is make sure that your plumbing and your pressurizing system works. So it's a test for that, and to make sure that your flow rates are what you want them to be.
So the measurements that we take is the ones you just described.
Yes, correct. And it's much safer than a hot fire because all the gases and stuff is inert. We'll be doing a cold flow on the new SFS before we send it out to get oxidizer cleaned. And oxidizer cleaned means that they literally take every component and scrub it down and use these crazy chemicals to clean it so that when we get it, it's vacuum sealed and has literally nothing on it besides the metal. And so there's no debris, nothing that can ignite, nothing that can blow up, nothing that can damage our system. And when we install it, we're going to install it with like latex gloves and really clean wrenches and a bunch of lubricants and stuff like that, so we don't put any foreign object debris, which is FOD, inside of our system. But you don't need to worry about that during the cold flow because nothing's going to ignite during the cold flow. So that's why we test with the cold flow. We make sure everything works. We'll take a bunch of pictures, label everything, and then send it over to them to go clean.
It's also a way to just go through procedures. So in case somebody does mess up, you're not working with like explosive, compounds
Yeah.
and stuff like that.
It's practice, basically. Any other questions before I go into the solenoids?
Yeah. In order to maintain the constant pressure, would you have to continuously supply the nitrogen?
Correct. So that nitrogen bottle feed system is always open
Okay.
during
Okay.
the hot fire and during the cold flow. Yes.
And so the purge system is basically just to purge anything out of the engine. If we
Right.
need to.
Have you guys seen the injector before? It has a flat plate and has a bunch of tiny holes in it. Those can get clogged with propellants. And so what the purge for the kerosene side seeks to do is kick all those extra propellants out. And for the liquid oxygen side, it seeks to push the remaining, after we close 353 on the top bottom right, after we close that oxidizer valve, you're still going to have propellants sitting inside that line between your engine and that closed valve now. So you need to make sure that those have a reason to go through your engine. So you turn on your purge to push out the remaining propellants. That's what it does, to prevent liquid oxygen from sitting inside our system and our pores. That's why you purge. Any other questions? These are all good. Cool. Any questions about ball valves, check valves, pressure relief valves, gauges, thermocouples, pressure
Can you
transducers?
explain thermocouple again?
Yeah, so thermocouple, do you take ME 170 eventually? No? I think Aaron had a good way of explaining it. Aaron, you want to explain it?
Yeah, so from my understanding, remembering about what they talked about in 170 was that you kind of have like two pieces of metal that are close together at the tip that are made of different metals. Like one's going to be like copper, one's going to be something else. And because they're different materials, they have different properties, and you're going to get a potential across the two metals just from having a temperature. I'm not sure. So there's like the Seagrass effect.
Seebeck
The Seebeck effect, yeah.
Yeah. So look up the Seebeck effect, and that'll explain.
They're really simple. They look like freaking two horsehairs, and that's it. Right?
Yeah.
Yeah. All right. So now I'm going to go into the last part of the system. This is a basically cutoff system from the rest. You can see that it has a different feed. It says compressed gas, 150 psi. Does everyone know what an air compressor is? Basically, you turn it on, it uses electricity, and it takes a bunch of air from the atmosphere and pressurizes it down for us, and then we can like shoot it out wherever we want. We're going to plug an air compressor into our solenoids, and all of these three-way solenoids is basically what they do is they allow that compressed gas to flow into our pneumatic spring return actuators, and so that we can actuate our valves from afar. So basically, if we didn't have this solenoid system, we would have to be on top of our valves turning them by hand. But with these solenoids, they take an electric current, we send electricity to them, they open up, they let pneumatic gas through, and that pneumatics is going to turn our ball valves for us while we're in the bunker. It's basically a safety precaution. You do not want to be anywhere near this system when you fire it. And so, dang, okay. So basically what happens is that we're just going to plug it up into that compressed gas tank, and it's going to split off in 8 different directions. And you'll notice that there's an Orifice CG540, CG440. What we're going to be doing is that when you open that pneumatic ball valve, 250 and 350, you don't want it to open instantaneously. If that opens instantaneously, you are sending a lot of pressure or nitrogen gas into the top of your tank pretty fast. And so what that's going to do by putting a choking orifice there, it's going to open that spring return really slow. And we're okay with it opening slow as long as it closes fast. So that's all it's going to do. It's going to open slow so that we don't pressurize our tank really fast and geyser or anything like that. Are there any questions on the solenoid system? It's basically the compressed gas system, 500 series.
So you have both the regulator and the ball valves, 250 and 350, pressurizing your tank slowly?
Yes. So what happens is that the regulators let flow rate through at a fixed amount. We can't affect the regulator flow rate. What we can affect is how fast that pneumatic ball valve opens. And so we're going to open it slow so that when it lets out that, like, honestly, these regulators can't go down to 5 psi. They'll probably go down to 100. So we'll start at 100. So when it opens with 100 psi, it'll open pretty slowly. And so that way we don't hit our propellants with a 100 psi brick. Cool.
So the pressure,
Good. So a regulator takes high pressure and regulates it down to a low pressure. And then a pneumatic actuator takes air pressure to turn a valve 90 degrees, open or closed. That's what an actuator does.
and the compressed gas is just to basically affect the actuator.
Yes, the compressed gas will never interact with the nitrogen gas, and it will never interact with the propellants. It's only going to stay on top of these.
Okay, so it never enters the system.
It never ever enters the system. That's why we're okay with it being dirty compressed gas, because we never have to worry about it getting anything dirty or anything like that. All right. So for those of you on the SFS refurb team doing calcs and stuff like that, we basically need to just calculate from our flow rates and everything exactly how we need everything to be situated. For those of us on Vulcan, we need to make a new PID. So we'll be figuring out how exactly we want the press system and the propellant system to work. And for those of you on CubeSat monoprop, you guys need to make a test stand. It's monoprop, one propellant. And so it's only going to have one half of this system, basically. Any further questions about flow control, how propellants work? I'm going to talk about fittings and how we get actually tubing around and stuff like that.
We use silencers. I was reading what the NASA engineers talked about,
Yes.
and silencers don't really go into these because they're coupled with solenoid valves or.
Silencers or orifices?
Never mind.
Okay. All right. Okay. All right. So the way tubing works is that you'll have all this hardware. So if you look at pneumatic ball valve 353, it looks like this with the big ass stem on top of it and one of these Thor's hammers on top of it. And so we'll put compressed gas into this. It'll turn a stem, and that stem will turn the ball for us. That's basically how it works. You can see it on the SFS right there if you want to see it. more up close. That's how those ball valve assemblies work. And in each ball valve, we tend to order them with threaded ends. So if you look at this ball valve, it has threaded ends on the inside. That lets us interface it with tubing and other hardware. So threaded ends, this is a certain type of thread called National Pipe Thread, NPT. The way these are made is CNC or a tapered thread. As you get closer and closer, deeper in, the threads get closer together. And what that allows is for more compressive stresses, so it can handle higher pressures. So that's why we use NPT. It can handle really high pressures. The issue with NPT is that they can leak a lot, so you need to put like Teflon tape around the threaded ends. And so what we like to use is it's AN, Army, Navy, or AS fittings. If you guys look at just, I'll show the camera for this. If you guys just look at the top half of this, so up here, you can see that there's a 37-degree taper. And what that 37-degree taper is that when you put a flared fitting on a flared tube, we have a flarer that goes at 37 degrees. When you put two flares together like this, when you put a flare and flare together, they actually have a really good tight seal. Flares, when you compress them together, they hold really tightly. And so what you do is that ANs have threaded fittings just like the NPT. What you're going to do is you're going to take a flared tube with a nut and a sleeve. So this is called a sleeve. This is called a sleeve. This prevents your nut from falling off. So this big nut right here, which has threads on the inside of it. Okay. So sorry, I can't show you everything, but this sleeve prevents the nut from sliding off. So the sleeve for this pipe right here is right here. You can't see it because it's underneath, but there's a sleeve right here that prevents the nut from sliding off the flare. And so what you're going to do is that you're just going to take your tube, you're going to attach it to that flare, and then you're just going to be able to tighten this, and you're going to be able to wrench tighten this. And you don't need any Teflon tape or whatever what I was talking about with the NPT stuff, because these flare seals are really tight. So you don't need to worry about any leaks or stuff like that. You can leak check it other ways. And so you just wrench tighten that afterwards. And so that's how we interface tube with hardware. And this NPT end on this would just go into a ball valve or something like that. Yes, so that's about it. We're probably going to buy our new ball valves with AN ends, so we don't have to worry about NPT, FOD, or anything like that. But it doesn't really matter. The tubing diameters we use are accordance to mass flow rate. So you just need to do a bunch of math basically to figure out your tube diameters, how big to make your valves, how to size your valves, how to size your regulators. We'll be doing those calculations today. Any further questions about the PID, plumbing in general, flow control, anything like that? Cool?
Good job, John.
Thank you. All right. All right, thanks everyone for listening. Your PIDs are for you to keep. I hope you guys, because when we're out to the Mojave, a lot of people like to ask us questions like, how does this thing work? I hope everyone will be able to answer those questions. Like, why do you have this regulator here, for example? And we can explain, like, okay, we would regulate it down and we go to the oxidizer system or something like that. So that way you guys are just like semi-comfortable with how this works. Sound good?
Yeah.
Cool. All right, thank you guys for listening. I hope you learned a lot. If you have any questions, feel free to ask me.